Hello, everyone, and thank you for joining us today. My name is Michael Evangelista, and I will be your moderator for this webinar. Just a few reminders that you are in listen-only mode to avoid unnecessary background noise. However, you can type in your questions anytime you want, and those questions will be answered by our panelists in a Q&A segment. By the way, the recording and certificate of this webinar will be sent out in 2 days' time, and our topic for today is about closer testing. It is a pre-recorded webinar from our colleague in the US. So without any further ado, let's start this webinar. Ray?
Hello, everyone, and thank you for joining us today. Welcome to Megger's monthly webinar series. Today's topic is basics of recloser testing. And on the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. You will receive an email within about 2 business days of the webinar, and that email will include a copy of the PowerPoint presentation and and a link to the video recording of the webinar if you'd like to watch it again or share it with your colleagues. Remember, you can ask questions at any time during the presentation, and they will be answered at the end of the webinar during the Q&A session. All right, our presenter today is Abel Gonzalez, Megger Relay Applications Engineer. Okay, let's go ahead and get started. Thank you for joining us today, Abel.
Okay, guys. Like Jamie said, today we are going to talk about recloser testing. Here's a short overview of what we will be covering today. We'll be talking about why do we use reclosers on the network, how do reclosers work, what are the advantages of using reclosers, what are the definitions associated with the reclosers in power systems and the power system terminology, the types of reclosers that are available, the applications of those, and how do we test them. And then at the end, we'll give a short introduction to recloser test set that we have. Now, why do we need reclosers on the network? Well, the main reason for that is that the vast majority of the faults in a power system are not permanent. By not permanent, I mean faults that have the characteristic that they clear themselves, like a tree branch falling on a line. It creates a short circuit, and it only lasts for as long as that tree branch remains between the lines, and then as the tree branch falls to the line, the fault clears itself. Other examples are animals that accidentally touch 2 faces of the system, a kid flying a kite whose tail sometimes touches the lines, other types of, lightning strikes, the effect of wind, rain, snow. Many things create temporary faults. And when those temporary faults happen, if you have the classical old, and I'm talking very old mechanism of clearing the fault and then sending somebody there to look for it, then you waste a lot of time, you waste a lot of money. So somebody came with the idea of what if we clear the fault initially because there is a fault in the system, and then we wait and reclose. So we energize that circuit again, so that if the fault was a transient fault and it was cleared, well, then everybody is back in business. Everybody has service again, and you don't have to send anyone there. And you cut a lot of time in the clearing of the fault, and you save a lot of people a lot of hassle, right? So how do reclosers work? Well, the working model of a recloser is you have some sort of controller, and you have a breaker, and that controller is helping the breaker perform its operation. Let's say that in this distribution line, a fault shows up, and of course the controller detects the fault, sends an opening signal to the breaker opens, and then everyone on the line is suddenly without power. But the controller, being the intelligent guy that he is, says, let me wait for a while and then reclose, because maybe that was a temporary fault and it cleared itself. But when it closes, the fault is still there. And since the fault is still there, the controller says, okay, let me open again. I have to open. There's a fault in the line, right? So it opens, does the same thing again, waits, because, maybe the time that it gave the first time it was open wasn't enough for the fault to clear, and it closes again. And it repeats that cycle for a maximum of around 4 times until it determines whether the fault is there to stay or if the fault cleared itself. In this case here, we are showing a case where at the end of the 4th shot, the controller finally determines that the fault was a permanent one, and it has no choice but to remain permanently open. In this case, well, the utility has to send somebody there to check, see what was the reason for the fault, clear the fault, repair, do whatever repairs are necessary, and then put everyone back in service. But if at any time during this cycle, when there is a closing, the fault had disappeared, then everyone would have had service without the need for any human intervention or the waste of time for both the utility and the customers who are would be without power. Right? Now that we've seen how the recloser works, we can see or talk about the definition of the recloser. Now, if you remember, we saw that the recloser is a combination of a controller and the circuit breaker. Okay? The controller gives the circuit breaker the ability to reclose or to close onto lines that were previously open without the intervention of a human, without the intervention of anyone on that operation. So the auto recloser can be defined as a circuit breaker with an automatic closing mechanism, or like Wikipedia defines it, is a circuit breaker equipped with a mechanism that can automatically close the circuit breaker after it has been opened due to a fault. The ANSI device number for the auto reclosing relay is 79. Those who have had contact with this, whenever you see the 79 function on a relay, that relay has the capability of performing reclosing operations. Okay. Now, how do reclosers look in real life? Well, in real life, you have the breaker, which contains also the sensors that the reclosers have. Initially, reclosers, when they came to existence prior to World War II, the reclosers were mainly overcurrent devices, and because of that, they only had current sensing capabilities, and they had no idea what the voltage was on the system. Right now, modern reclosers have the ability to sense both currents and voltages, and not only that, they have the capability to sense voltages on both sides of the breaker, so that they can perform synchronizing functions or voltage induced functions for automation in the system. Now, this is another example of a recloser. This would be a recloser when it is installed in the pole. You have up here the high voltage part of the recloser, and then down here you have the control cabinet that contains the controller, and it also contains, well, the communication mechanisms that are integral to reclosers today. Now, in some, actually in a lot of the literature, you find that the recloser is defined as only this part. They call this part the recloser, and then this part the controller. I I don't like that definition. I would rather say that the recloser is the whole thing, because this part cannot perform the reclosing functions without the controller. That's something that is a little bit confusing, and it leads to confusions when it comes to the definitions of tests that you have to do to a recloser, because in some cases, people get confused and say, no, if I have to test a recloser, it's only the high voltage part that I have to test. And that is just not true. In my opinion, it's better to define the recloser as the whole thing. And then, yeah, it has two parts, and both parts need to be tested to some extent, right? This is another example of a recloser. This is a recloser being taken out of service and when a new recloser is being installed. And here you have examples of recloser controls. Different manufacturers have different relays used in the recloser control. Now, to be fair, I'm only putting here examples of recloser controls that you can find in a cabinet. In some cases, the recloser is integrated in a single unit that so that the recloser control and the recloser mechanism are all installed in the tank, and there's no way to separate them. Okay. In those cases, usually the controller is activated by the energy that circulates through the line, and it doesn't have an alternate power source. So I'm not here. I am not presenting examples of those types of reclosers, which are fairly common in the field as well. Now, the advantages of using reclosers, well, they minimize the interruption time in the system, and therefore increase the revenue for the utility. The less time you have customers without power, the more you're charging those customers. You restore the system capability and critical system interconnections. It maintains the system stability. Reduces a lot of manpower, yeah, because you don't have to send people to every single fault out there. If you remember the statistics that we gave at the beginning of the presentation, 80% of faults in the system are transient. I know those numbers they vary from 60 to 90%, but anyway, most people agree that a good number for the transient fault is about around 80%, which means that in reality, you only have to take care about 15 to 20% of the faults in the system. Hence, you reduce a lot of manpower by the use of this simple yet very powerful scheme of automation. You allow substations to run unattended, and of course, you improve customer satisfaction. Now, the reclosers, even though they were created 70 years ago, they allowed the power system to show the early stages of intelligence. Today, we talk about smart grid, and we talk about artificial intelligence, and systems and things coming alive and presenting stages or signals of intelligence. Well, in the 1930s, when these technologies were invented, the system was already showing systems of, signs of intelligence by the simple means of allowing a mechanism to reclose itself without the intervention of a human being. Now, the recloser itself is composed of, let's say, three parts that operate in conjunction. You have a protection relay. Sorry about that. You have a protection relay, okay, which contains the 79 element, but which has a lot of protection functions of its own that operate independent of the 79 element. And also you have the circuit breaker, which is the mechanical, the muscle of the recloser. Now, when a fault happens, the protection relay initiates a counter, and then it operates. The counter is usually the time that it takes for the fault to go from the inception of the fault to the operation time or the trip time. Sometimes it is what's called instantaneous or with no intentional time delay, or sometimes it's a simple time function. What I'm trying to say here is that there is some time between the moment when the fault shows up and the moment when the operation is initiated. Now, after the operation is initiated, the circuit breaker takes some time to go through its cycle. The coil is energized, the contacts separate. When the contacts start separating, an arc shows up, and then that arc is quenched, and then the contacts fully open. That takes a little bit of time. And then after that time, you see that there is no current. The relay realizes that there is no longer current in the system, and then it resets its protection function and starts waiting again to see if there is another event in the system. Now, during that time, the 79 element is initiated. The 79 element is initiated at the same time that the protection relay initiates its operation for the first fault that happens in the system, right? Now, the 79, remember, the 79 is smart. He sees one fault, and after it sees that fault, it waits for the opening, and then after a few moments, tells the breaker to close again. All right? So the 79 waits until there is an opening, until the breaker opens. All right? Sometime after the breaker opens, the 79 initiates again the closing, right? So after the breaker opens, it waits for some time and then sends a signal saying, hey, I believe this time is enough for the fault to clear, so please close the breaker. Now, the breaker closes, all right? The breaker closes, and in this case that I'm showing here, the closing happened against a fault. Now, let's say that this 79 element was a single shot element, meaning that it was only programmed to close once. What that means is that if you see a fault, the relay, of course, will say, hey, open again because there is a fault. Now, what that means for the 79 is that it will go to what's called relay lockout. Lockout means I am no longer going to reclose. I am going to wait until somebody comes, fixes this, and resets my operation. For a successful operation, then you have the same things in the beginning. You have a fault. You have the circuit breaker opening. All right. Then you have the 79 issuing the close command here. And then there is a time that the 79 element waits before it resets. Why does it wait for this time? Well, because if there is a fault in this time here, the 79 will continue in its current reclose cycle. But if there is no fault during this time, after this time, the 79 resets and starts a new reclose cycle. Now, this time here, between the moment when the close command was issued by the 79 and the resetting of the 79 function is called reset time, reclaim time. It has different names and different languages. But the essence, the thing to take here is that is the time that takes for the 79 to reset its shot counter on the presence of no fault in the system, right? Now, this brings us to a few definitions. I guess I've gone through all of them already. You have the operating time, which is okay from the inception of the fault to the trip coil energizing. That's from the relay perspective. For the circuit breaker's perspective, that's from the moment when the relay commands the circuit breaker to open to the moment when the arc is quenched and the contacts are fully open. Then you have the dead time, which the most important one here is for the 79 relay, is the time from the recloser scheme initiation, which initiates with the first trip to the closed coil energizing. So it goes from when the relay trips to when the 79 says, I want you to reclose. It doesn't go from when the breaker opens to when the 79 detects the breaker close. No, it goes from the moment when the relay trips or the relay issues the trip signal to the moment when the 79 issues the close or reclose signal. The reclaim time, well, I already spent time explaining what the reclaim time means. Lockout means that there is not going to be any further action from the 79. The 79 is going to remain open, the circuit breaker is going to remain open, and somebody has to come and reset manually or remotely, reset the operation. That manually or whether manually or remotely depends on the philosophy of the utility that you're working for. In some places, manual operation is required. In some places, remote operation is permitted. Now, the number of shots is how many shots you are going to allow that recloser to have. The typical number of shots is 4. In some applications, you have 1 shot, and also when you're talking about the number of shots, you have to talk about how fast you want those shots to happen. Usually for reclosers, the first and sometimes even the second shot are fast shots, and then the third and fourth, if there are that many, are usually slower, either because you want to, and we'll see it later here, you want some fuse down the line to burn, or because you want to give more time to whatever is between the lines to burn itself, right? Now, when it comes to the types of auto recloser, I'm not talking up here about how do you build them. I'm not talking about oil or vacuum or no. Here, I'm talking from the operational perspective. What can they do in the system? When we're talking about types of auto recloser, we have the 3-pole reclosers or 3-phase reclosers, in which all 3 phases are operated regardless of the fault type. These are, I would say, the most common reclosers out there. I'm talking worldwide. They have their own advantages. You don't have to really discriminate faults between phases. Also, they have their disadvantages because sometimes the fault is in one phase, and then you leave everyone without power. And then sometimes when you do that, you're not really being as smart as you could be. Now, single pole operation is becoming more and more common because precisely they have less effect on the load, but they are also more complex. Although modern microprocessor relays can do phase discrimination very well, so it's not really, and of course they are more complex and expensive, but again, those differences are being eliminated as the time goes, right? Now, we can also discriminate the types of auto recloser between medium voltage and high voltage. Right here, my main focus has been on, and will be throughout the presentation, on medium voltage or distribution reclosers. A couple of applications. The first one is the one that I was talking about, the fuse save scheme. Now, you have the ability, remember, The auto reclosers today, they are powered by a very good brain, which is a microprocessor relay. Now, the microprocessor relay has the ability to change the way it operates for different shots of the recloser. From shot to shot, they can change how do they respond to the same fault. So, for example, you could have a fast curve for the first or even the second shot, and then you can, if the number of shots increases to either 3 or 4, then you can increase the time of operation for those other shots, right? The advantage of this is that if the first two shots are, if one of the first two shots is successful, then you save the fuses on that are downstream from the relay, because they don't have time to open, to burn themselves. But the other advantage is that you are trying to clear the fault as fast as possible initially, right? So since 80% of the faults are transient is usually fast. So this also allows you to clear most of the faults very fast. This is another advantage of this. The disadvantage is that you could give a temporary outage to larger customers connected in the feeder who may not have anything to do with the fault, because maybe the fault is downstream from them, right? So this could be a disadvantage of the fuse save scheme. The fuse blow scheme is the other way around. You only operate on slow curves. So in this case, you're always waiting for the fuse to blow before opening and then sequentially reclosing. The advantage is that, well, you're not making pay, someone who has nothing to do with the fault for the fault. But the disadvantage is that you always have to replace the fuse. Now, the 79 function can be blocked by a number of reasons. And the first thing is that the 79 is usually only started by the main protection function of the relay, and it can be blocked by a number of things. The one that, in my opinion, is very important is that you don't want to reclose when there is a manual operation of the circuit breaker. So when you have a manual operation, or even sometimes a remote operation, again, depending on the philosophy of the utility that you're working for or with, you don't want the recloser to act when a manual operation of the circuit breaker was indicated. Because if you do a manual operation, it's because you want the recloser or the circuit breaker to remain open for as long as you want, and then you want to be yourself the one who closes it. You don't want some automation, so you need to reclose the circuit while you're working on it. That's why you need to have the ability to block the 79 whenever you're doing operations on the breaker or on the circuit. Another reason for blocking the 79 is when there is a circuit breaker fail. The breaker failure function detects discrepancies between the status of the breaker as it is fed to the relay and the actual circulation of current through the feeder. And it can even detect, depending on how you program it, discrepancies between the status of the circuit breaker signal fed to the relay and the remote instance of that same signal that's being read by the SCADA function. Things like that can, because you have an ambiguous state, prompt the blocking of the recloser operation. Another application of reclosers is when you have something like this, where you have two feeders with 3 reclosers. There could be more. I just chose 3 on each feeder for the sake of the example. And then those feeders are connected by a normally open tie here, which happens to also be a recloser. If there's a fault, for example, between 2 and 3, recloser 2, which is the one upstream from the fault, remember the feeder is on the left side, detects the fault, goes through its cycle. It means open, close until, okay, it's a permanent fault. When it is a permanent fault, I remain open. After the feeder, the recloser number 2 goes through its cycle, propagates the state of that recloser through the network, telling everybody, hey, I'm open because I saw a fault downstream from me. Every other recloser on the same network here, or on the broadcast list of those messages, is now aware of the status of recloser number 2, which means that recloser 3, since it knows that recloser 2 opened because of the fault, now starts getting ready to receive power from feeder 2, which remains unaffected, right? So he opens its breaker because he doesn't want feeder 4, recloser 4, the tie here, to close onto a fault. Now, 7 does some calculations. Can I take the extra load given the state of the load right now? Remember, I'm the first one here. I'm the one that are more charged. I may even have to change my settings group to take all that load. Yes, I can. Well, if you can, then 4 now closes its breaker, given the fact that he knows what happened to 2, he knows what 3 did, and he also knows that 7 enabled his operation by telling him, yeah, you know what, the feeder can take the load, and now there may even be a settings group on reclosers 6 and 5 in order to take the extra load that's being served. Now, this allowed the system to recover itself without the intervention of any human. The system, again, showing system signs of intelligence. Now, in this case, I presented an operation that happened using communications between the relays, but this could also happen without the use of communication, although I guess it's not the preferred way right now, but it's a kind of algorithm that can also be implemented, because all this operation can happen only by the fact that the reclosers 2, 3, and 4 detect changes in the status of the voltages on both sides of the line, right? Again, reclosers allowing the power system, and this plays very well with smart grid implementations and whatnot. And remember, here I didn't say which protocol was being used to propagate the communication, the information between the relays. It could be a proprietary protocol, or it could be something as advanced as the 61850 used to propagate the communication. Also, I didn't talk about the medium. You could have radios between all of the reclosers. You could have radios on one side and fiber optic on the other. This has nothing to do neither with protocol nor with the medium used for the propagation of the communication between the protocols. It can be implemented in many different ways, being such a simple but yet, in my opinion, powerful idea. Now, testing reclosers is a messy business, right? You have to disconnect the tank or not, depends. But if you don't disconnect the tank, then you have to inject a high current. You have to stay in the sun. You have to you have a lot of configuration settings, software, etc. that you have to deal with. And why do we test reclosers? Well, there's a bunch of different reasons, right? Most important ones is that most utilities nowadays have adopted reliability indices to evaluate the quality of the power that they are providing to their customers. I'm not going to explain the differences between SAIDI, SAIFI, KD, MAFI. I guess That's something that right now is common knowledge, but just to know that utilities have to respond sometimes to regulatory bodies. They have to respond to them, and they have to keep these indices within acceptable parameters, right? Acceptable limits. So remember that using reclosers keeps customers more time, powered more time. But if the recloser fails, then the operation of the recloser is not successful. And why does the recloser fail? Well, and a lot of times because we didn't use the proper maintenance schedules and procedures with them. Now, the other reason, NERC requires that you test reclosers. There are several documents on NERC that tell you how often do you have to test reclosers, and what are the recommended tests, and if it's going to be a time-based maintenance schedule, and what are the frequencies and things like that. So from the standards point of view, you are required to test reclosers, but also to improve customer satisfaction. I guess this is the most important part. None of these things have any value unless you look at it from the side of the customer. Now, testing reclosers. How do you test them? Remember, we're going to see what a couple of pictures of reclosers right now. But I guess that when it comes to options, you have to choose. How do you want to do it? You have to choose if you're gonna use primary injection or secondary injection. In some cases, you could even use both. In some cases, you have no choice but to use primary injection because of the type of recloser, the procedures that you have in place. But in some cases, you have the choice of using secondary injection, right? Again, it depends on which test equipment and recloser you have and the type of tests that you're going to perform on them. Now, primary current injection, well, it's true. It tests the entire mechanism because you are injecting current on the primary and you're verifying operation of the recloser, which means that you don't have to worry about separating the controller from the recloser. You don't have to test the sensors on the recloser independently. It's one way of doing it. Now, remember that, in my opinion, this goes well when you have reclosers that have mainly current sensors and don't have any voltage sensors. Because when you have voltage sensors, how do you test them using primary injection? It's kind of hard. I guess you can do it, and there are I'm sure, ways that have been developed for that. And it's also primary current injection not suitable for fully testing the distribution automation functions, because the number and scope of tests that you can perform using primary current injection is a little bit limited. It's also, I guess, easier. It doesn't take as much training. You don't have to deal with a lot of the settings. I guess there are a lot of advantages of primary current injection as well as disadvantages. The test sets tend to be bulkier. You're dealing with a lot more energy. It's something to take into consideration. Now, on secondary current injection is the preferred method, in my opinion, to test the controller. You can use it when it is possible to separate the controller from the high voltage unit, which is something that more and more reclosers today allow you to do. It's very flexible because you can be as creative as you want with the test plans. Remember that when you're doing this, testing the recloser is very, very similar to testing a protection relay, and all the tools that you have for testing protection relays you can use in this scenario. It is suited to test the distribution automation functions, and well, most modern reclosers can be tested this way. What do you test when you're talking about testing the recloser? Well, you mainly test the protection, the sequence of operation. You check that the times are correct. You check that the communications between the recloser and the other reclosers in the system, or the recloser and the remote unit are correct. You test the schemes. Remember, we talked about distribution schemes. Schemes, by the way, is one of the things that NERC requires you to test as well. You test coordination between different reclosers, and you can perform, if you're using scheme test, you can perform end-to-end tests. Other things you test are the breaker, the sensors, things that I'm not mentioning here because I'm not focusing on those tests during this. It would be too long, I guess, presentation. When you are faced with testing the recloser, which is connected to in the pole where you have the control cabinet here, and you have the actuating mechanism or breaker in the pole, there is usually a cable that connects that mechanism with the control panel. What you have to do is you have to get in the way of that cable so that you can take the signals from the panel, use this from those signals, use what you want to use to feed the relay, okay, and feed the relay with the signals that you want to use from your test set without having those signals to go through the circuit breaker mechanism. Now, that sounded a little bit too abstract, so I'm going to put it a little bit more clear. You have the mechanism here, and the mechanism has the sensors. The sensors have the CTs and PTs, or resistive sensors, that bring the analog signals into the relay. Okay? Now, if you want the relay to operate, you have to inject those analog signals to the relay. One way of doing it is opening the cabinet, disconnecting the relay. If you look here, usually the connections on the back of the relay are a mess. Messing with them is very dangerous because you could make an error after you finish your test. So the best way is to simply interrupt the cable. You're not breaking anything. You simply disconnect that cable that comes from the top, and you connect the cable of your own over here, all right, so that you can inject into the relay the analog signals that you want the relay to respond to. But you can also use the breaker status signals that come from the breaker to feed them into the relay, so that the relay has the feedback from the breaker that it needs to perform its operation. Remember that reclosers are very sensitive to breaker status. They are very sensitive to discrepancies between the breaker status and the status of current through its analog inputs. So you have to be aware that you need to feed the relay with the proper breaker signals. Otherwise, the test will be compromised. You will not be able to do the test properly. Now, one way is like this. Again, bringing the signal from the unit into some test set and then feeding the relay. This way you can use analog signals from a test set, and you can use the digital signals directly from the breaker and feed it into the relay. Sometimes, however, you do not want to test the mechanism. Sometimes you only want to test the controller. In those cases, you can use a tank simulator, and you can connect that tank simulator directly here to a connection box or a test set that can take the analog signals, all right, and provide a feedback into the relay of what's the status of the breaker signals. Or you could simply use a test set to simulate those breaker signals. All right. So I guess those are the three in general options that I like. There are probably other options out there, but the thing is that the most important thing to take into consideration here is that when you're testing the controller, you have a bunch of signals that you have to feed into the controller so that the controller operates properly. Remember, the controller only operates and the only thing it does is it reacts to stimuli from the outside world, and the stimuli come in the form of analog signals, breaker contacts, and then the controller sends out signals like trip, close, sometimes enabling and disabling signals, and it also sends communication. That's why the most important thing is to be able to feed into the controller and take then signals from the controller. This cable here not only takes signals into the controller, but also brings the trip and close signals into the real world, right? After you have the connections figured out, all you need to do is get some sort of test set that allows you to create a test plan with as many states as you need to test the recloser. Remember, the recloser operates discretely. It sees a fault, it trips to the fault, right? See the ball, hit the ball. It sees the fault, trips, waits, closes. If it closes and there is a fault, trips again, closes again. If it closes and there is no fault, it waits until the reclaim time has been elapsed and resets the mechanism. But if there is a fault, then it trips again, and so on. So what you need to do for those tests is, and in this case, I'm using, of course, our software with where I was able to program different states to which I gave names like pre-fault. Here I'm simulating using this binary input. This binary output from the test set. I'm simulating the breaker status. When there is a pre-fault, the breaker status is closed. State 2 is a fault. I'm injecting a fault of 5 amps. Remember, I made this up. I'm not. It's not a real case scenario, but in any case, what I did is when I have little current or no current, the voltage is going to be 69. When I have a higher current, the voltage is going to drop. Okay, and in this case, still you have a breaker open because this is the moment when the relay sends the trip signal. After the trip signal has been sent, the breaker opens. So I have this binary input, output open, and I wait for some time before injecting current again into the relay. All right. I receive the closed signal here, and when I receive the closed signal, I change states and so on. This allows me to go to trip 2, then another state of reclose, which means idle or no current being injected into the relay. Again, breaker open in this state, and again it's waiting for this binary input, which comes from the trip signal that comes from the relay, to close again. All right, and in this case, I'm again closing onto fault, and again opening, closing onto fault again, and then I'm going to lock out. All right. Again, I'm not saying you have to use the Megger test set. I guess you have to use a test set that allows you to create different states and one state for each of the conditions that you want to test on the relay. The only fault that I tested here was a three-phase fault, 5 amps on each phase at 0, 120 to 40. You can test for different types of faults, and actually you should test for the most common faults in the system, which are single phase to ground faults and so on. Don't create test plans only for the 3-phase faults. Test whatever is required, but also test smart so that you can test different scenarios. How does the test plan look? Well, you have current increases or current increments every time the relay closes. There is a fault, and there is a fault, and then you have voltage dips every time there is a fault. You have a binary output activation, The binary, this binary is um, closed here. Higher up, okay. Open here, and then you have the binary output 1, and then you have the binary inputs, and the binary inputs are only 1 and 2, and I'm using binary inputs for trip and close signal. And also you have the timers. And of course, this is, I guess, the most important part. So you created your test plan and you ran your test. You need to be able to recover the times. You can set your timers, or you should be able to set your timers. Again, doesn't matter which test set you're using. You should be able to set your timers. In this case, I'm simply using change of states as the start and stop conditions. I could use binary inputs. It depends, I guess, in what do I want to test. So in this case, I'm timing the trips and reclose times and all the time to log out. I could test, in this case, I only tested 4 shots with a permanent fault. I should be able to test, I don't know, a couple of shots with a non-permanent or transient fault. Remember, don't be limited to 1 or 2 types of tests. Try to test as smart as you can. Now, this is another, okay, so far, we've only tested the recloser on the pole with no connection to anyone in the outside world. But what happens when we have what we showed you before, a system like this, where the different reclosers operate in unison to respond to states in the system? Well, in this case, what you would do is you could do something like this. You could show up at each of the reclosers with a similar setup simultaneously and do a synchronized test, or what is known as a end-to-end test. There is another webinar by Megar a couple of years ago about end-to-end, and there's a couple more. So I'm not going to go into end-to-end testing, but I guess what I'm trying to say here is that when you're testing a scheme for reclosers, you could take advantage of the possibilities that today's technology allows to do synchronized tests. It doesn't have to be GPS, the time signal. It could be some sort of network timing protocol if that's available in the locations that you are that you have your reclosers. I know of cities that have a fiber optic cable to each of the reclosers, but I know other places where they have no such thing and they still have automation. So I guess it depends on where you are at. You don't even have to show up, like in this case, with 7 different test sets in 7 different locations and do all the tests at the same time, unless you are really required to do it. In this case, for instance, I guess testing 3, 4, and 5 synchronized, or even 2, 3, and 4, or I guess doing a test to 2, 3, and 4, and then to 3, 4, and 5, and probably 6, 5, and 4. So I guess you could test this system with only 3 or even 2 if you want to test the tie and all of the against all the others, things like that. But you do need to figure out, if you have some automation, you need to figure out a way of doing of performing tests synchronized. Okay. Now, when it comes to connections, we have different possibilities in the reclosers. Let me go back to the. Just a second. This is something I didn't think. It was poor thinking on my part. The cable here is not. It has different ways. It has different forms. It's not always a round cable of 14 pins or 32 pins or whatever. There are sometimes square connectors or different types of connectors. What I'm trying to say is that you need to figure out a way to connect your recloser to whatever test set you have, because there is no test set out there that has a universal connection. Most test sets, they have a connection on the test set, and then you need some sort of adapter to connect. Now, the most popular cables are, no doubt, this 14, 19, and 32 pins. These ones you can connect directly into this test set here. And remember, you have the connections to the control, and then on the back of the test set, you have the connections to the tank, right? This is the Megar ERTS. I guess this is the last part of our presentation. It's a unit that allows you to interface with the control unit using a test set, using which you can inject current into this current inputs here, put voltage into this voltage sources here, and those currents and voltages will be fed into the controller via one of these control cables here. You can also use the the binary inputs and the binary outputs to simulate the status of the breaker and to get signals from the relay and into the test set, or you can use the cable connection to the tank to bring signals from the controller to the tank. As a summary, we have talked about how the recloser improves the reliability and stability of the system, improves revenue, very important. It improves customer satisfaction. The success rate of reclosers is high. 80% of the fault clearance happens in the first shot. Remember, I was talking about how most of the times you have the first shot as a fast shot. Of course, that depends on the application, the place where you're connected and whatnot. It can be used for system automation and smart grid applications, and well, testing reclosers is a NERC requirement. There's a couple of sources that I have for you here. On the presentation that I'm going to send out, I'm going to include a lot more sources so that you guys have it there. Jamie, I guess I'm done here.
All right, so that's the end of the presentation, everyone. So if you have any questions, you can type in now in the chat box and we'll answer it for you. But before doing that, I just want to remind you that there will be a pop-up survey form that will pop up on your screen when you close this webinar box. Please fill up that survey because that will really help us a lot in improving our webinars. Okay, so let me see the questions. Oh, we don't have questions at the moment. So guys, if you have any questions, we will give 1 minute for you to type in the questions, or 2 minutes. And yeah. For the presentation copy and the recording will be sent out in 2 days' time. Uh, how much is Recloser, sir? Sorry, I don't have any idea for the I'm not sure from what country are you, but yeah, I'm not sure of how much the Recloser is. But yeah, so some reclosers, if I may give you some brands, we have what do you call that? From Australia, we have the I forgot, but we have ABB, we have Cooper, um, I forgot the other brand from Australia, but that one is also a good one. But yeah, I don't have any idea of how much is it. So I guess we don't have any questions at the moment. So we can now conclude this webinar. And at this point in time, I would like to say thank you everyone for joining us today. And we hope to see you again next time in our future webinars. So again, thank you so much, guys. Have a good day and please stay safe. Thanks, Grace. Thanks, Mehdi.
Thank you, Michael. Bye bye.
Bye bye.